Hi all, today I'm going to be talking about triangle similarity proofs. Now let's talk about the word similarity itself. Now, the word similar means that two things share some characteristics, and the geometrical term itself is not far away from um, that English definition. So if I draw a triangle and then replicate that, paste. Now what I've constructed is two triangles which are exactly the same. Now if I decrement the size proportionately with that tool there, I have this triangle here. Now they're not exactly the same in terms of just sheer size, but they do seem to have same angles, as you can just tell by inspection, and the sides are in proportion to the larger triangle here. So the term used to describe the relationship between these two triangles is called similarity. Now you indicate the symbol for similarity is three upright straight lines like 111. Nelson. So these two triangles are similar. Now I'm going to be constructing a square. Let's use the color red. Now there we have a square. I'm going to be replicating that square over here. I've constructed two congruent squares. Now if I were to increase the ratio, these two squares are no longer congruent. Now they're similar because they share the same angles, as you can tell. All angles are 90 degrees. And the sides seem to be in proportion. What do I mean when I say they're in proportion? So say if that side was 4, that side is 5. Let's say 8, even though it doesn't look 8. That side would be 4, that side would be 8, and so on. Since all the sides in a square are exactly the same, that would be 4 and that'd be 8. That would be 8 as well. So I've just scaled this square by a factor of 2, so basically increasing the dimensions by 2. It was a 4 by 4, now it's an 8 by 8. So these two shapes or these two squares are going to be similar to each other. Just using the mathematical term similar here. If I were to construct two circles, these two circles would be similar. No matter, the only requirement for two circles to be congruent is for them to have exactly the same radius. As you can tell, these two don't have exactly the same radius. This can be bigger, and this one has a smaller. But as you can tell, this circle here seems to be a scaled up version of this one here. So these two shapes are, I think they're just too big there. These two shapes are similar to each other. Now lastly, if I construct a pentagon, that seems like a fancy shape. Okay, so there's a almost regular pentagon. Now if I replicate the pentagon, now I have two congruent pentagons. Now if I were to scale this down or up, let's scale it up. These two pentagons would be what? These two pentagons would be similar to each other since I've just scaled this one up to this one. The angles are preserved, as you can tell. This angle would be equal to this one. This angle here would be equal to that one there. and so on for that one and that one and that one. Okay. Now, I think I'm going to be introducing the formal proofs for similarity in triangles, which is often studied at school. So the first one is angle, angle, angle. Did I say it thrice? Yeah. Okay, so it's angle, angle, angle. Okay, so if I were to construct a triangle, like so, and simply replicate it here, these two would be congruent, as you can tell easily. Now if I were to scale this down, these two angles would be the same. You can just tell by inspection, and you can actually drag this on top of that and tell that angle's exactly the same. Those two angles are exactly the same, and those two angles are exactly the same. So if two triangles have three angles which are exactly the same to the corresponding angles in the other triangle, both of those triangles are going to be similar to each other. Now there's a shorthand method of actually using this proof. You can actually shorten it down to angle, angle. So say if this angle were to be equal to that angle, and this angle here were to be equal to that angle, they'd still be similar to each other without having, well, if these two angles were exactly the same as each other, the corresponding ones which I've drawn out, this one to that one, this one to that one, were exactly the same, they would just automatically mean that these two top angles would be exactly the same due to the angle sum of a polygon, the internal angle sum of a polygon, and which is 180 for triangles. So if I were to construct another, well, actually, let's just rub out these ones here. Okay. Now say this angle here was 45. This angle here was 60. It doesn't look like it. They're obviously equal, but just for the sake of this exercise. Now, these two triangles would be similar. How can we tell? Well, from the angle sum theorem of a triangle, we can tell that this side is going to be 75, and this side, when I said side, I meant this angle is going to be 75 degrees, and this angle here, if we work out, that's 105, plus, let's call that x. 105 plus x equals 108. Subtracting 105 from both sides, x equals 75. So that x is going to be 75. So now we know if two corresponding angles in two triangles are the same, in our case 45 and 45, 60 and 60, then the third side is automatically going to be the same as the top one. I mean, when I say the top one, but the remaining angle. Now the next theorem is if you have two sides in equal ratios with an included angle, jeez, I spelled that wrong. That was meant to be angle, you can tell. Okay, I need to learn how to spell. Okay, so this is going to be SAS, but this is not to be confused with the SAS in congruence. SAS is also congruence proof, if you didn't know. Okay, so if I have two triangles, again, we're dealing with triangles, bear with me. Let's create them red. Okay, let's have a weird triangle. There we go. Now, let's say that this angle here, let's actually replicate that first because we would need another triangle. I'm going to scale this up. Okay. This triangle has that angle equal to 60, that side equal to 2, and that side equal to 1. This triangle here has that angle equaling 60, that side equaling 8. Doesn't look like it, but let's just assume that's 8. That side over there, and that side is 4. Now, what does the first part of the proof mean? Two sides in equal ratios. Well, we can construct a ratio and find out. So these two seem to be corresponding sides. Let's use them. 2 is to 8. Well, that just simplifies to 1 is to 4. And the next ratio, 1 is to 4. Well, that's exactly the same as this one here. So we have two sides in exactly the same ratio. And we have an included angle, which is equal. So these two triangles would be similar. Last proof, finally. Okay, three sides in equal ratio, side, 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 SSS, but this is not to be confused with the congruence SSS. The congruence SSS is not to be confused with this one. This states there must be an equal ratio. The congruence says they must be exactly the same. That's just a side note there. Okay, so there must be an equal ratio. That's the bit we need to be concerned with. Okay, now if I replicate this triangle, and then scale it down. Oops. Okay, now let's say that this side here is 100 centimeters. This side here is also 100 centimeters. And this side is 200 centimeters. No, that wouldn't work, would it? And this side would be 150, let's say, centimeters. This triangle here has it as 50, 50, and this side is 75. Let's just say they're all centimeters. Looks like a CN. Okay. Now, again, we are trying to look for equal ratios, so let's construct ratios for corresponding sides. Well, we can match this one, this side here, with this side. This side seems to be lining up with that one. And lastly, the last side lining up with the another bottom side. Okay, let's construct some ratios. So it's going to be 100 to 50, and this just simplifies to 2 is to 1. The next ratio, again, 100 is to 50. This simplifies to 2 is to 1. Lastly, 150 to 75. This also simplifies to 2 is to 1. And there we have it. Since these ratios are exact, are equal there. In fact, equal. These two triangles would be congruent. I mean, not congruent. I mean, they would be similar. And the symbol for it is, again, the 3 upright vertical dashes, or lines if you like. And hope that helps. Thanks for watching, guys and gals.